In 1950, Enrico Fermi posed a question during a discussion at Los Alamos National Laboratory that remains unresolved. Where is everybody? The Fermi Paradox arises from the apparent contradiction between high probabilistic estimates for extraterrestrial civilizations and the lack of observational evidence. The Milky Way contains hundreds of billions of stars, many significantly older than the Sun. If even a small fraction host habitable planets that produce intelligent life, technologically advanced civilizations should have emerged long before humanity. Given sufficient time, potentially hundreds of millions of years, such civilizations could theoretically explore or colonize large portions of the galaxy. However, astronomical observations reveal no confirmed signals, artifacts, or large-scale astro-engineering structures. This discrepancy between theoretical expectation and empirical observation constitutes the paradox. Over the decades, researchers across astronomy, biology, physics, and philosophy have proposed numerous explanations, ranging from rare life hypotheses to self-limiting technological civilizations. Despite extensive investigation, no single resolution has been empirically validated, leaving the paradox an open scientific problem. The scale problem. The Fermi paradox is only as disturbing as the scale of the universe is properly understood. Most people who encounter the paradox understand it intellectually, but do not feel it viscerally, because the numbers involved are so far outside human experience that they fail to generate appropriate intuitions. Establishing the scale correctly is not preamble. It is the argument itself, because the case that the silence is anomalous depends entirely on whether the universe is large and old enough that we should, by conservative calculation, expect to see evidence of other civilizations. The Milky Way contains between 200 and 400 billion stars. The uncertainty range in that estimate is itself larger than the total stellar count that astronomers believed existed when Fermi asked his question. Those stars are distributed across a disk roughly 100,000 light-years in diameter, approximately 1,000 light-years thick at the Sun's position, with a central bulge several times thicker and a halo of globular clusters extending much further. Light, travelling at 300,000 kilometers per second, the fastest speed permitted by physics, takes 100,000 years to cross the disk from edge to edge. A car travelling at highway speed without stopping would require approximately 2 quadrillion years to make the same trip. 2 quadrillion is 2 million times the current age of the universe. Inside this disk, planets are not rare, they are the default. The Kepler Space Telescope, which monitored approximately 150,000 stars for 4 years, searching for the slight dimming caused when a planet passes in front of its host, established that planet formation is a nearly universal accompaniment of star formation. Essentially, every star in the galaxy has at least one planet. Most have several. Extrapolating from Kepler's statistics to the full stellar population of the Milky Way gives a total planetary count measured in the trillions. Of those trillions, the number orbiting in the habitable zone of their star, the range of distances where surface temperatures could permit liquid water, is estimated at between 5 and 40 billion, depending on assumptions about habitable zone boundaries and the habitability of planets around different stellar types. Even the conservative end of that range is 5 billion worlds where the chemistry of life could in principle begin. The temporal dimension compounds the spatial one. The Milky Way formed approximately 13.5 billion years ago. The Sun formed 4.6 billion years ago, meaning the galaxy had been producing stars, planets, and potentially running biospheres for nearly 9 billion years before the solar system existed. Stars that formed in the galaxy's early history could have hosted rocky planets that solidified 10 to 12 billion years ago. On Earth, life appeared within roughly 700 million years of the planet becoming habitable. If life on those early planets followed a similar timeline, those biospheres have been running for 10 to 11 billion years. Complex multicellular life appeared on Earth roughly 600 million years ago. Anatomically modern humans appeared 300,000 years ago. Technological civilization, defined as the ability to manipulate the physical environment in coordinated ways, has existed for perhaps 10,000 years. Radio technology, which makes us electromagnetically detectable across interstellar distances, has existed for 130 years. Now run those numbers on a civilization that formed around a star born in the galaxy's first 2 billion years. If their timeline from planet formation to radio technology paralleled ours, they achieved radio capability approximately 9 to 10 billion years ago. They have had 9 to 10 billion years of technological development since that point. 10 billion years ago on Earth, the only life was prokaryotic bacteria in shallow seas. The gap between 130 years of radio technology and 10 billion years of post-radio development is not merely large, it is categorically incomprehensible. The difference between a hand axe and a smartphone represents roughly 3 million years of human evolution. A civilization 10 billion years ahead of us has had 3,000 times that interval. What such a civilization would look like, what it would be capable of, what trace it would leave on the galaxy is genuinely beyond human imagination. The colonization timescale provides the most concrete way to see why the silence is strange. A civilization using spacecraft traveling at 1% of the speed of light, conservative by any projection, could colonize the entire Milky Way in approximately 10 million years, assuming centuries at each star system for colony establishment and ship construction. 10 million years sounds large until you recognize that it is 0.07% of the galaxy's age. The entire colonization timeline fits into galactic history roughly 1,350 times. A single civilization that began an expansion program at any point in the last several billion years should have descendants in every star system in the galaxy by now, including this one. Not probably, by straightforward arithmetic. And yet there is nothing. No confirmed signal. No artifact in the solar system requiring an artificial explanation. No star in our galaxy whose properties require the inference of megastructures. No galaxy in surveys of hundreds of thousands of external galaxies whose infrared signature indicates civilization-scale energy harvesting. The silence is not a gap in a noisy signal. It is total, consistent, and confirmed across multiple independent lines of observation spanning the full electromagnetic spectrum and beyond. That is the scale problem. The universe is old enough, large enough, and planet-rich enough that the absence of any visible civilization requires a causal explanation. Everything that follows is an attempt to provide one. The Drake equation was never meant to give an answer. In 1961, astronomer Frank Drake organized a small conference at the National Radio Astronomy Observatory in Greenbank, West Virginia, to discuss the search for extraterrestrial intelligence. To structure the conversation, he wrote a formula on a chalkboard. It expressed the number of currently active communicating civilizations in the Milky Way as a product of 7 terms: the rate of star formation, the fraction of stars with planets, the number of habitable planets per planetary system, the fraction of habitable planets where life actually emerges, the fraction of life-bearing planets where intelligence evolves, the fraction of intelligent species that develop detectable technology, and the average lifetime of such a civilization. He was explicit that the formula was not a calculation, it was an agenda, a way of breaking an enormous, apparently intractable question into smaller pieces that could be addressed one at a time as scientific knowledge improved. In the 6 decades since Greenbank, 3 of those 7 terms have moved from speculation to measurement. The rate of star formation in the Milky Way is now well constrained by astronomical surveys at approximately 3 solar masses per year, translating to a few new stars annually. The fraction of stars with planets is now known to approach 1. Planet formation is standard, not exceptional, and the Kepler mission established this conclusively. The number of potentially habitable planets per stellar system is less certain, but the estimates, based on Kepler statistics and refined habitability models, suggest the number is at least of order 1 for Sun-like stars, and possibly higher for red dwarfs if their habitable zone planets turn out to be genuinely habitable despite tidal locking and flare activity. The remaining 4 terms have not moved in 60 years. They remain as uncertain as they were when Drake first wrote the equation, and they are precisely the terms that determine whether the final answer is a large number or a small one. The fraction of habitable planets where life emerges, the abiogenesis fraction, is unknown by any rigorous standard. Earth is the only data point, and from a single data point, you cannot calculate a probability. Life appeared on Earth relatively quickly by geological standards, within a few 100 million years of the planet becoming habitable, which is sometimes interpreted as evidence that abiogenesis proceeds readily wherever conditions permit. But this reasoning commits a subtle statistical error. If abiogenesis were extremely rare, requiring perhaps 1 attempt per billion years of planetary habitability, we would still expect to find ourselves on a planet where it succeeded simply because we could not exist on a planet where it did not. Our existence cannot be used as evidence that our existence is likely. This anthropic selection effect is a genuine obstacle to interpreting Earth's history as a sample from a distribution. The fraction of life-bearing planets that develop intelligence is comparably uncertain. Complex animal life has existed on Earth for roughly 600 million years. Of the millions of species that have lived and died in that interval, exactly one, the genus Homo, and within it one specific lineage, developed cumulative technological culture. Every other branch of the animal kingdom, including many with sophisticated cognition, did not. Dolphins, great apes, corvids, and elephants all demonstrate problem-solving, social learning, and behavioral flexibility that exceeds what most species possess, but none of them invented writing, metallurgy, or radio astronomy. The ratio of technologically capable species to total animal species in Earth's history is approximately 1 in several million. Whether this ratio reflects an intrinsically rare biological achievement or merely the contingency of which specific lineage happened to cross a threshold that many others could have crossed is not resolvable from the data. The final term, the average lifespan of a communicating civilization, is the most consequential and the most unconstrained. Its importance is enormous because it enters the equation multiplicatively, and its plausible range spans many orders of magnitude. A civilization that destroys itself within a few centuries of developing radio technology contributes almost nothing to the time average population of communicating civilizations in the galaxy. A civilization that survives for millions of years dominates the calculation. Difference between these scenarios, multiplied across thousands of potential civilizations, is the difference between a galaxy with thousands of active communicators and a galaxy with effectively none. We have been broadcasting for 130 years and have not yet destroyed ourselves, which is one data point from which nothing statistically meaningful can be extracted. What the Drake equation has accomplished in the 60 years since Greenbank is not the calculation it superficially resembles, but the intellectual organization it was always intended to provide. It identifies exactly which questions need to be answered before the Fermi Paradox can be resolved. The astronomical questions, star formation, planet frequency, habitable zone occurrence rates, are now answerable and are being answered. The biological questions, abiogenesis probability, complexity evolution rates, intelligence frequency, are the frontier of astrobiology and will be addressed by the next generation of telescopes searching for biosignatures in exoplanet atmospheres. The sociological questions, technological civilization lifespan, expansion behavior, communication choices, remain essentially unapproachable from current data. Every proposed resolution to the Fermi paradox is, at its core, a claim about which of the unknown terms in Drake's equation is dramatically smaller than the optimistic estimates assumed. The Great Filter. The most conceptually powerful framework for thinking about the Fermi paradox was proposed not by an astronomer or a biologist, but by an economist. Robin Hanson published his 1998 paper, The Great Filter, Are We Almost Past It?, in response to what he saw as a failure of the existing literature to confront the logical structure of the problem directly. His contribution was to recognize that the silence of the galaxy is not merely an interesting puzzle, but a hard logical constraint, and to formalize what that constraint implies. The Great Filter is the name Hanson gave to whatever step or steps in the sequence from dead chemistry to interstellar civilization are so difficult, so improbable, or so lethal that virtually no lineage of matter in the universe successfully navigates them. The universe began 13.8 billion years ago with hydrogen and helium. In principle, the process that started there could end with visible, galaxy-spanning civilizations. The fact that we observe no such outcome, despite billions of years of time and trillions of potentially habitable worlds, means something is preventing the process from completing. That something is the filter. It could be a single catastrophic improbability or a series of individually unlikely steps whose product is vanishingly small. The form does not matter. The existence is a logical requirement of the observation. The filter's location relative to our own position in the sequence is what gives the concept its existential weight. There are two possibilities, and they are as different as hope and doom. If the filter is behind us, embedded in our past, in some step we have already navigated, then the silence is explained by the rarity of what we have accomplished. Perhaps abiogenesis is extraordinarily rare and most habitable planets remain sterile indefinitely. Perhaps the transition from prokaryotic to eukaryotic cells is a near impossible accident that happened once on Earth and almost nowhere else. Perhaps the specific sequence of extinctions and ecological upheavals that drove primate intelligence is so contingent that it almost never repeats. Whatever the specific step, if it lies behind us, we are survivors of a cosmic lottery. The galaxy is silent because most lineages of matter never reach our level. We are the extraordinary exception. The stars are ours to explore, if we can manage not to destroy ourselves, and the galaxy's emptiness is not a warning, but a testament to how lucky we were. If the filter is ahead of us, the situation reverses completely. In this version, the steps up to and including our current level are not rare. Life arises readily. Complex cells evolve, multicellular animals develop, intelligence emerges, technological civilization forms. Thousands or millions of species across the history of the galaxy have reached a point similar to where humanity now stands, with radio telescopes and nuclear weapons and dreams of the stars. And then something kills them, every single one. Something universal, something inevitable, given sufficient technological development, something that no civilization in the history of the galaxy has yet survived. The silence is not the sound of absence. It is the sound of a wall struck over and over across billions of years by every species that developed the ambition to get past it. The asymmetry between these two scenarios generates the most counterintuitive implication in the entire Fermi Paradox literature. The discovery of life on Mars, or in Europa's ocean, or in the atmosphere of a nearby exoplanet is bad news. Each such discovery implies that the origin of life is not rare, that it happens readily wherever conditions permit. That pushes the filter forward, away from abiogenesis and toward our future. Every step toward intelligent life that we demonstrate is not rare, is a step that cannot be the filter, which means the filter must lie somewhere else. The only somewhere else is the future. A galaxy full of dead civilizations, each of whom reached something like our current level before being destroyed, would look exactly like the galaxy we observe, and each piece of evidence that the early steps are easy tightens the argument that the late steps are fatal. This is why some researchers have a complicated relationship with the excitement around astrobiology discoveries. Finding biosignatures in the atmosphere of a habitable zone, exoplanet, would be one of the greatest scientific achievements in history. It would also be, if the Great Filter framework is correct, evidence that the thing waiting in our future is both real and lethal. The discovery that we are not alone might simultaneously be the discovery that we are doomed. Hansen's framework does not identify what the filter is. It is a logical structure, not a physical theory. Identifying the specific barrier, whether it lies in the distant past of biological improbability or in the near future of technological self-destruction, requires the detailed analysis of every candidate's step in the sequence from chemistry to civilization. That analysis occupies the remainder of this script. Rare Earth. In 2000, paleontologist Peter Ward and astronomer Donald Brownlee published Rare Earth: Why Complex Life is Uncommon in the Universe, arguing that the popular conception of a galaxy teeming with complex life was inconsistent with the specific conditions that Earth's history reveals are necessary for it. The book's central thesis was a distinction that has since become central to astrobiology. Simple microbial life and complex multicellular life are not points on a single continuum. They are separated by a gulf of conditions so specific and so improbably satisfied simultaneously that the two categories may be separated by many orders of magnitude in cosmic frequency. Microbes may be common. Animals may be rare. Intelligence may be extraordinarily rare. The argument begins with location at the galactic scale. The Milky Way is not a uniform environment. Near the galactic center, stellar densities are high, supernova rates are elevated, and gamma-ray bursts from neutron star mergers and collapsars periodically sterilize the surrounding volume. The radiation environment near the center is hostile to the long-term persistence of complex surface biospheres on geological timescales. The outer galaxy, by contrast, is metal-poor. The heavy elements needed to build rocky planets and the biochemically essential elements of life are less abundant, where fewer stellar generations have processed primordial hydrogen and helium into heavier nuclei. Between these extremes lies a galactic habitable zone, a band at intermediate galactic radii where stellar density is low enough to avoid frequent sterilizing events, and metallicity is high enough to permit rocky planet formation. The Sun sits within this band. The stellar type matters as much as the galactic location. The Sun is a G-type main sequence star with a stable luminosity output that has varied by only a few percent over 4.6 billion years. This stability is not universal. The most common stars in the galaxy are M-type red dwarfs, which are cooler and smaller, but which are prone to violent flares that emit intense bursts of ultraviolet and X-ray radiation. Planets in the habitable zones of red dwarfs are, by necessity, much closer to their stars than Earth is to the Sun. At these distances, tidal locking is likely. One hemisphere permanently faces the star in perpetual daylight, while the other faces away in permanent darkness. Whether complex life can develop on a tidally locked planet is uncertain. The atmospheric dynamics, the temperature gradients and the radiation environment are all substantially different from Earth's, and there is no empirical basis for assuming that these differences are neutral with respect to biological complexity. The planetary magnetic field is a prerequisite whose importance was demonstrated by Mars. Earth's magnetic field, generated by convection of liquid iron in the outer core, deflects the solar wind, the continuous stream of charged particles ejected by the Sun. Without this deflection, the solar wind gradually erodes a planetary atmosphere through a process of charge exchange and sputtering that strips atmosphere into space over geological timescales. Mars once had a magnetic field generated by the same mechanism, but its smaller mass meant its interior cooled faster. When the core solidified and convection ceased, the magnetic field died. The solar wind then stripped the Martian atmosphere over hundreds of millions of years, transforming a potentially habitable world with liquid surface water into the cold, dry desert observed today. The maintenance of a planetary magnetic field over billions of years depends on the heat budget of the planetary interior, which is itself sensitive to factors including the planet's mass, its radioisotope inventory, and the energy delivered by any major impact events in its history. The Theia impact, the collision between the young Earth and a Mars-sized object approximately 4.5 billion years ago, threads through multiple aspects of the rare Earth argument in ways that reveal how tightly coupled Earth's habitability factors are. The impact created the Moon, and the Moon's gravitational influence stabilizes Earth's axial tilt. Without this stabilization, dynamical modeling suggests Earth's axial tilt would vary chaotically between near zero and much higher values over millions of years, producing climatic instability that might have prevented the development of complex ecosystems. The same impact reheated Earth's interior, contributing to the long-term maintenance of a convecting liquid outer core and therefore the magnetic field. It also delivered additional radioactive isotopes, primarily uranium, thorium, and potassium-40, that have been providing radiogenic heating to Earth's interior for 4.5 billion years, contributing to the geological activity that drives plate tectonics. A planet that never experienced a Theia-equivalent impact might have cooled more quickly, lost its magnetic field earlier, and failed to develop or sustain the tectonic system that regulates long-term climate. Jupiter plays an additional protective role that the rare Earth hypothesis identifies as potentially important. Its gravitational dominance over the outer solar system perturbs the orbits of asteroids and comets that would otherwise cross the inner solar system at higher rates, deflecting many of them onto trajectories that eject them from the solar system entirely. Without Jupiter's influence, the frequency of large impact events on Earth would be significantly higher, potentially disrupting complex ecosystems repeatedly before they could achieve the stability that permits the long evolutionary trajectories leading to intelligence. Whether Jupiter's protective influence is essential or merely beneficial is debated, but its role in shaping the impact history of the inner solar system is not. Stack all of these conditions simultaneously: galactic habitable zone location, stable G-type host star, strong magnetic field maintained over billions of years, a large stabilizing moon produced by a specific impactor geometry, plate tectonics sustained by an appropriate radiogenic heat budget, a giant planet guardian in the outer system, and liquid water on the surface for geological timescales. Each condition has some probability less than 1 of being satisfied for any given planet. The rare Earth argument holds that the product of these probabilities, when compounded across all conditions simultaneously, is very small, possibly small enough to explain why the galaxy appears empty of complex life, even if it is abundant in microbial life. If the fraction of planets satisfying all conditions simultaneously is 1 in a billion or less, the nearest world with complex life might be thousands of light years away, its signals too faint to detect, its megastructures too distant to image. The hard steps. The rare Earth hypothesis addresses the environmental conditions necessary for complex life. The hard steps argument addresses the biological transitions within an already habitable environment that are individually so improbable that they dominate the probability calculation of reaching intelligence. Even given a planet that satisfies every environmental criterion, galactic location, stellar type, magnetic field, moon, plate tectonics, the emergence of technological civilization requires a sequence of biological innovations, and the evidence from Earth's evolutionary history suggests that at least some of these innovations are so difficult that they required an amount of time comparable to the age of the biosphere to occur. The logic of the hard steps argument, formalized by evolutionary biologist John Maynard Smith and astrobiologist Urs Satmari in their 1995 book The Major Transitions in Evolution, and extended quantitatively by astrobiologists including Nick Bostrom and Milan Čirković, proceeds from a specific empirical observation. Some biological innovations that appear in Earth's evolutionary history occurred only once, while others occurred many times independently. The frequency of independent occurrences is a proxy for difficulty. An innovation that evolved dozens of times independently, like the eye, which evolved in perhaps 40 separate animal lineages, is not a hard step. It is an accessible solution to a common evolutionary problem. An innovation that occurred only once in 4 billion years of Earth's history, despite enormous population sizes and generation times that collectively represent a vast number of evolutionary experiments, is a hard step by the most natural definition. Abiogenesis is the first candidate hard step. The origin of life from non-living chemistry remains incompletely understood despite decades of experimental effort. Individual components of the process have been demonstrated. Amino acid formation under plausible prebiotic conditions was shown in the Miller-Urey experiments in the 1950s. RNA's ability to catalyze chemical reactions, including aspects of its own replication, has been established, and lipid membrane formation from simple fatty acids is a well-characterized self-assembly process. But the complete sequence from simple organic chemistry to a self-replicating, metabolizing entity capable of Darwinian evolution has not been demonstrated in any laboratory, and the probability that all necessary steps occurred in the right sequence, in the right environment, within the window available on a young planet is unknown. It could be high, meaning life begins wherever conditions are right. It could be vanishingly small, meaning Earth was extraordinarily lucky, and most habitable planets remain sterile indefinitely. The transition from prokaryotic to eukaryotic cells is the second candidate hard step, and in some respects the most compelling one. Prokaryotes, bacteria and archaea, cells without a membrane-bound nucleus and without the complex internal organelle architecture that characterizes all visible life, dominated Earth's biosphere for approximately 2 billion years after the origin of life. 2 billion years is a long time. In that interval, prokaryotic populations numbered in the quintillions, generation times were measured in hours, and the accumulated number of evolutionary experiments was effectively incomprehensible. Prokaryotes diversified into almost every metabolic strategy, colonized every accessible environment, and drove significant geochemical cycles, including the Great Oxidation Event. They did not produce eukaryotes, cells with nuclei, mitochondria, and the internal complexity that makes large, differentiated multicellular life possible. The eukaryotic cell arose, as far as the evidence indicates, in a single event. One archaeal cell engulfed a bacterial cell and, rather than digesting it, retained it as a permanent internal symbiont. That internal bacterium eventually became the mitochondrion, the organelle that powers essentially every eukaryotic cell alive today. All eukaryotic life on Earth shares a single mitochondrial ancestor, which is the phylogenetic signature of a single endosymbiotic event. In 2 billion years of prokaryotic evolution, with population sizes and generation times that accumulated more evolutionary experiments than any human number system is equipped to express conveniently, this specific merger occurred exactly once. The waiting time argument is powerful. If the transition were readily achievable by natural selection, you would expect it to have occurred multiple times independently, as photosynthesis did, and as antibiotic resistance does, and as countless other adaptations do. Its apparent singularity is strong evidence that it required an unlikely event, not merely an available adaptive pathway. A 2024 paper in the journal Nature by evolutionary biologists Andrew Roger and colleagues provided updated phylogenetic analysis of the eukaryotic transition, confirming the single origin interpretation and adding detail to the specific archaeal lineage involved. The host was an Asgard archaeon, a member of a recently discovered archaeal superphylum with unexpectedly eukaryote-like genomic features. And the symbiotic event involved a specific type of proteobacterium that contributed not only the energy-generating mitochondrial function, but also significant amounts of genetic material that was incorporated into the eukaryotic genome. The specificity of the required partnership, this particular archaeal lineage, this particular bacterial type, in an environment that permitted the symbiosis to be stable rather than digested, is consistent with the view that the transition required a low probability convergence of specific conditions. Sexual reproduction, the development of animal body plans, the colonization of land, and the development of large nervous systems capable of learning are each further steps in the sequence, each of which might individually be difficult. But the quantitative argument for hard steps focuses on the steps that are most clearly documented as singletons. A single quantitative framework developed by Bostrom and extended by astrophysicist David Kipping in a 2020 paper attempts to infer the number of hard steps from the timing of major biological transitions relative to the total habitable window available on Earth. The analysis finds that the data are most consistent with somewhere between 3 and 10 genuinely hard steps in Earth's history. If there are 5 hard steps, each requiring an average of 1 billion years to complete, the expected time for a planet to produce intelligence is 5 billion years, close to what Earth actually took. Planets with shorter habitable windows, produced around shorter-lived stars or in planetary systems that lose habitability earlier, would not complete the sequence before their window closes. Most would get stuck at some intermediate step. Why intelligence may be a fluke. The hard steps argument treats intelligence as one endpoint of a multi-step biological process and estimates its probability from the frequency of the individual steps. But there is a deeper version of the same argument that challenges a more fundamental assumption: that intelligence is a predictable or expected outcome of evolution on a productive biosphere given enough time. The assumption is embedded deeply in most public discussions of the search for extraterrestrial intelligence and in the optimistic end of Drake equation calculations. It holds that evolution, given sufficient time and a complex enough biosphere, will tend to produce intelligence, because intelligence confers such strong survival advantages that natural selection will consistently favor its development. This assumption is not derived from evolutionary theory. It is imported from an intuition that mistakes the product for the inevitable output of the process. Evolution does not have goals. It does not move toward intelligence or toward any other property. It moves toward reproductive success in a specific environment through the blind mechanism of differential reproduction of heritable variants. A trait is favored by natural selection when it increases the expected reproductive output of organisms that carry it, relative to those that do not, in the environment where selection is operating. Intelligence, defined as the general capacity for flexible behavioral response to novel situations through learning and reasoning, is metabolically expensive. The human brain constitutes approximately 2% of body mass and consumes approximately 20% of total resting metabolic energy. That cost is paid continuously throughout an organism's life, regardless of whether the intelligence is being used at any given moment. Natural selection favors intelligence only when the benefit, improved survival and reproduction through behavioral flexibility, exceeds this continuous cost. In environments where behavioral flexibility does not confer large advantages over specialized, lower-cost cognitive solutions, natural selection will favor the cheaper option. Most environments on Earth do not favour the evolution of human-grade general intelligence. Insects have been the most numerically and biomass-dominant animal group for hundreds of millions of years, using neural architectures with fewer than 1 million neurons that implement highly specialised behavioural algorithms requiring no general reasoning capacity. Fish have dominated aquatic environments for 400 million years, with relatively modest cognitive elaboration. Reptiles thrived for hundreds of millions of years before mammals displaced them, without developing anything approaching primate-level cognition. The evolutionary success of these lineages demonstrates that sophisticated intelligence is not the only solution to the problem of surviving in a complex environment, and that in many environments it is not even the best solution. The evolutionary biologist Stephen Jay Gould argued repeatedly over his career that the history of life is radically contingent, that the specific outcomes we observe are products of a specific historical sequence of events, and that replaying the evolutionary process from any earlier starting point with even minor differences in initial conditions would produce radically different outcomes. Intelligence is not a fixed point that evolution converges on from any starting position. It is one of an essentially infinite number of possible outcomes, reached by one specific lineage through a sequence of events that included the mass extinction that ended the dinosaurs, the specific paleoclimatic history that drove primate diversification in Africa, and the particular anatomical inheritance that made fine manual manipulation available to the hominin lineage as a tool for extending cognitive ability into the physical world. A 2023 analysis by evolutionary biologist Walter Veit applied evolutionary game theory to the question of when general intelligence is a stable evolutionary strategy. The analysis found that high general intelligence is evolutionarily stable only in a relatively narrow range of environmental conditions, specifically conditions where the environment changes rapidly and unpredictably on ecological timescales, forcing behavioural flexibility because no fixed behavioural strategy can adequately track the variation. In stable environments, specialised cognitive strategies outcompete general intelligence because the lower metabolic cost more than compensates for the reduced flexibility. In the limit of very high environmental variability, general intelligence is favoured, but so are other high-cost strategies that may not converge on human-like cognition. The implication for the Fermi Paradox is that a biosphere running for hundreds of millions of years on a stable, hospitable planet might consistently produce sophisticated life without ever producing technological intelligence, simply because the environmental pressures that favour general intelligence over specialised cognition are uncommon and contingent. Technological intelligence may require not just a productive biosphere and sufficient time, but a specific ecological and paleoclimatic history, the equivalent of the Theia impact for biology that most productive biospheres never experience. Self-destruction as the default. The great filter does not require life or intelligence to be rare. It has a version in which life and intelligence are common. Civilizations arise routinely throughout the galaxy, and the filter lies not in the distant past of biological improbability, but directly ahead of us, in the developmental stage we currently occupy. In this version, every civilization that reaches our level faces the same set of challenges, and most fail them. The galaxy is not a nursery that never produces children. It is a nursery where the children reliably destroy themselves. Nuclear weapons represent the most historically demonstrated pathway to civilizational self-destruction. The physics of nuclear fission and fusion is universal. It follows from the properties of atomic nuclei, which are the same throughout the cosmos. Any civilization that develops a sophisticated enough understanding of atomic structure will discover nuclear reactions, and the military applications are a near inevitable consequence of the energy densities involved. There is no known path from pre-nuclear physics to a mature understanding of atomic structure that bypasses the discoverable weapons application. The knowledge that produces nuclear power also produces nuclear weapons. The human case study is more informative than is usually acknowledged in Fermi Paradox discussions, because the Cold War produced not merely the existence of nuclear weapons, but documented near-miss events in which civilization-ending exchanges were nearly triggered by specific, reconstructible mechanisms. The Cuban Missile Crisis of 1962 has been extensively analysed as a case study in the dynamics of nuclear escalation. What the declassified record reveals is that the 13-day crisis involved at least 3 distinct moments when decisions made by specific individuals on the basis of incomplete information nearly resulted in nuclear exchange. The Soviet submarine B-59, cut off from communications with Moscow and under depth charge attack from American naval vessels, carried a nuclear torpedo whose launch required the agreement of 3 officers. 2 agreed to launch. The third, Captain Vasily Arkhipov, refused. The deterrence framework that supposedly governs nuclear conflict depends on rational actors with accurate information and clear communications. The actual dynamics of the Cuban crisis involved neither. In 1983, Soviet officer Stanislav Petrov was the duty officer at a Soviet missile early warning station when the system reported a launch of 5 American Minuteman IJCBMs. The protocol required him to report the detection up the chain of command, which would have triggered a response. He judged the detection to be a false alarm. The number of missiles was too small to be a genuine first strike, and he suspected a system malfunction and reported it as such. His judgment was correct. The detection was caused by a satellite misidentifying high-altitude sunlight reflections off clouds as missile exhausts. The system's malfunction had not been encountered previously. Petrov's decision to override the protocol was based on reasoning rather than evidence. Had a different officer been on duty, or had Petrov been less confident in his assessment, the outcome might have been different. The same year, NATO conducted a command post exercise called Able Archer 83, simulating a nuclear release procedure that was sufficiently realistic to be interpreted by elements of Soviet intelligence as possibly covering preparation for an actual first strike. Documents declassified in the 1990s and 2000s revealed that the Soviet leadership's concern about American intentions in this period was higher than American intelligence understood at the time, and that the exercise generated genuine alarm in Moscow. The probability of a miscalculation-driven exchange was non-zero. Climate change operates on a different mechanism and a different timescale, but points toward the same structural problem. The cognitive and institutional machinery that produces powerful technology is not automatically the machinery that manages its consequences. Industrial civilization's reliance on fossil fuels made atmospheric chemistry alteration a byproduct of technological development that accumulated for decades before the scientific understanding of the consequences was developed, and then continued to accumulate for further decades after the consequences were understood, because the coordination mechanisms needed to change course were slower than the economic incentives to continue. Whether this represents a filter depends on the severity of the consequences. Climate change is disrupting civilizations without obviously destroying them so far. But the structural pattern of a technology outrunning its management is the same pattern that nuclear weapons demonstrate. Artificial intelligence as a self-destruction mechanism received its most rigorous Fermi Paradox treatment in astrophysicist Michael Garrett's 2023 paper, which argued that the transition from radio-capable civilization to post-biological AI may be so rapid that it effectively truncates the period during which a civilization is detectable. Garrett's central observation is that the interval between the development of radio technology and the development of transformative AI may be extraordinarily short on cosmic timescales, He estimated on the order of 200 years for human civilization, and proposed this as a rough universal. If true, it means that any civilization advanced enough to broadcast detectable radio signals is also close to building AI systems capable of reshaping or replacing the civilization. The post-AI trajectory is unknown, but Garrett argued that several plausible outcomes, AI-driven optimization for non-broadcast generating goals, civilizational collapse following AI-triggered disruption, or voluntary withdrawal from physical activity into computational substrates, would all reduce or eliminate the civilization's detectable electromagnetic signature rapidly. The galaxy would be full of the ruins of radio-capable civilizations that were each astronomically detectable for a few centuries before the AI transition silenced them permanently. The zoo hypothesis. Every explanation examined so far assumes that the silence is real, that there are no advanced civilizations broadcasting detectable signals, or that civilizations are so rare that none exist within detectable range, or that they destroy themselves before achieving interstellar reach. But there is a completely different class of explanation for the Fermi Paradox. What if advanced civilizations do exist, know we exist, and are choosing not to make contact? In this class of explanation, the silence is not the silence of absence. It is the silence of deliberate restraint. The most developed version of this argument is the zoo hypothesis, proposed by Harvard astronomer John Ball in 1973. Ball looked at the structure of the Fermi Paradox and argued that the most logically consistent explanation for both the galaxy's age and the total absence of any contact is that advanced civilizations are deliberately avoiding us. They have the capability to communicate. They are aware of our existence, and they have collectively chosen, for reasons of their own, not to interfere with our development. The analogy Ball drew was to wildlife preservation. Human societies are aware of populations of animals living in environments where we could intervene dramatically, but choose not to. International agreements protect isolated indigenous populations from contact they have not chosen. Ecologists monitor ecosystems without disrupting them. In each case, the more technologically capable party withholds contact not out of indifference, but out of a principled judgment that contact would be harmful to the less developed party. Now scale this reasoning to the astronomical. A civilization millions of years more technologically advanced than us would have capabilities relative to us similar to our capabilities relative to the other species on Earth. They might regard us as we regard isolated tribes in the Amazon, with interest, with care, with a principled commitment to non-interference. We would be unaware of their observation. The absence of contact would not be the absence of watchers. Ball's hypothesis extends naturally to the concept of a galactic community with agreed norms of behavior toward pre-interstellar civilizations. Perhaps the most advanced civilizations, through some form of galactic governance, have established and enforced a policy of non-contact with developing species. Perhaps this policy is the price of admission to a galactic community whose benefits, access to shared knowledge, protection from the kinds of catastrophic risks that isolated civilizations face, are sufficient to ensure compliance. Perhaps civilizations that break the non-contact norm face consequences that make compliance rational for all members. The scientific community's primary objection to the zoo hypothesis is the uniformity of motive problem. For the zoo to function as an explanation for the total observed silence, every advanced civilization in the galaxy, not most of them, but every one, would need to adhere to the same non-contact policy without exception. In a galaxy that might contain thousands of independently evolved civilizations with different histories, different values, and different governance structures, universal agreement on any policy is difficult to defend by analogy with anything in human experience. We cannot achieve universal agreement among 195 nation-states on straightforward matters of mutual benefit. The assumption that every galactic civilization independently arrives at the same hands-off policy and maintains it without any defector is a strong assumption that the hypothesis itself provides no mechanism to satisfy. The Galactic Club response partially addresses this objection. If the earliest spacefaring civilization in the galaxy established a non-contact policy and had sufficient time and reach to enforce it across the galaxy before later civilizations achieved interstellar capability, the policy would not need to be independently derived by each civilization. It would be a pre-existing condition that later arrivals encounter, adopt as the price of joining the interstellar community, and maintain as a norm of behavior. This scenario requires only one civilization to have established the norm early enough, not universal independent agreement. It is more plausible than the alternative, though it still requires an implausibly high degree of compliance across an enormous diversity of civilizations over enormous timescales. The zoo hypothesis's most serious weakness is not the uniformity problem, but the absence of testable predictions. The hypothesis predicts that we are currently below some threshold that would trigger contact from watching civilizations, but it specifies nothing about what the threshold is, what we would need to do to cross it, or how long we would need to wait. It predicts that the silence will end at some future point, but provides no basis for predicting when. In the absence of any prediction about observable consequences, the hypothesis is consistent with any future observation. Continued silence is consistent with it. Eventual contact is consistent with it, and nothing we could observe in the near future would falsify it. A hypothesis that cannot be falsified is not scientifically useful, whatever its intuitive appeal. The dark forest. The zoo hypothesis posits benevolent restraint, advanced civilizations protecting us from contact we are not ready for. The dark forest theory posits something structurally different, not restraint motivated by concern for us, but silence motivated by fear for themselves. In the dark forest, the galaxy is not a protected preserve. It is a battlefield in which every player's dominant strategy is to hide and to destroy any player they find before being discovered themselves. The concept takes its name from the 2008 science fiction novel by Chinese author Liu Cixin, but its foundations are in game theory, the branch of mathematics that analyzes strategic decision-making among rational agents with competing interests. Liu presented the idea as fiction, but the logical structure is independent of its narrative framing, and it has been analysed in the academic astrobiology literature as a serious candidate resolution of the Fermi Paradox. The argument begins with three premises that are minimal and difficult to dispute. First, every civilization's primary interest is its own survival. Second, the resources available in the universe, matter, energy, space, are finite, and civilizations with expanding resource needs will eventually compete for them. Third, across interstellar distances, communication is slow and intentions are permanently unverifiable. A signal takes years or decades to cross the distance between star systems. There is no mechanism for real-time verification of another civilization's claims about its intentions, capabilities, or future behavior. From these premises, the game theoretic analysis proceeds with uncomfortable precision. When Civilization A detects the existence of Civilization B, it faces a strategic decision. If A communicates peacefully and B is also peaceful, both benefit from the exchange of knowledge and resources. If A communicates peacefully and B is hostile, A may be destroyed. If A preemptively eliminates B before B can respond, A removes a potential threat at some cost, but eliminates a risk. The expected payoff of preemptive elimination is positive whenever the probability that B might eventually become threatening is above some threshold. Since the probability can never be reduced to exactly zero, B might be peaceful now and hostile later, or might have a hostile faction that comes to power in the future. The threshold is always exceeded. The rational strategy is to eliminate any discovered civilization before it can become a threat, regardless of current apparent intent. If every civilization in the galaxy follows this reasoning, the equilibrium is universal silence and universal preemptive destruction of any civilization discovered to exist. The galaxy becomes a dark forest, in Lu's metaphor, a place where every hunter moves silently through the trees, armed, afraid, knowing that any sound will attract others who will kill them. The forest is silent, not because it is empty, but because the cost of making noise is lethal. The dark forest predicts a specific observable consequence for our own situation. Our radio signals have been expanding outward at the speed of light for 130 years, forming a detection sphere approximately 260 light-years in diameter. Any civilization within that sphere with the capability to monitor for electromagnetic emissions from developing technological species now knows we exist. We did not choose to announce ourselves. The announcement was an unavoidable byproduct of developing radio technology. The Arecibo message in 1974, the plaques on the Pioneer probes, and the golden records on the Voyager spacecraft added intentional announcements to the accidental ones. If the dark forest is correct, these actions were not aspirational gestures. They were potentially fatal errors. The academic analysis of the dark forest framework has found that it is not a universal equilibrium of game theory, but a possible outcome in a specific range of parameters. The outcome depends on assumptions about the distribution of civilizational values. What fraction of civilizations are aggressive versus cooperative by nature? The cost of interstellar strike capability relative to the economic capacity of the civilization, and the timescale on which a developing civilization could become a peer threat. When the cost of preemptive strikes is low relative to civilizational capacity, and when the timescale for a developing civilization to become threatening is short, the dark forest equilibrium is the game theoretic prediction. When costs are high or threatening timescales are long, cooperative equilibria become possible. The theory is neither inevitable nor impossible. It is parameter dependent. The deepest challenge for the dark forest as a complete Fermi Paradox resolution is the same challenge that faces all deliberate silence explanations. It requires essentially universal behavioral adoption. A galaxy where even a modest minority of civilizations chose cooperative rather than aggressive strategies would show evidence of those civilizations, their signals, their megastructures, their probes. The total silence we observe requires that the cooperative minority either does not exist or has been eliminated, which pushes the theory toward a darker version. The forest has been hunted clean, and what we see is the aftermath of a process of elimination that is perhaps still ongoing. We are searching the wrong way. Before drawing any conclusions from the silence, it is worth asking how thoroughly we have actually searched. The honest answer is that the search for extraterrestrial intelligence, despite 6 decades of effort and genuine scientific seriousness, has covered a fraction of the relevant parameter space so small that drawing strong conclusions from it borders on the statistically indefensible. The most frequently cited quantification of the problem comes from a 2018 paper by Jason Wright and colleagues at Penn State, who attempted to express humanity's total SETI effort as a fraction of the total search space. Their framework considered the search space as a multi-dimensional volume encompassing direction on the sky, distance, frequency, signal intensity, and time. When they estimated the fraction of that total volume that all SETI efforts combined had actually surveyed, the result was approximately equivalent to searching 1 bathtub of water out of all the Earth's oceans, and concluding on that basis that the oceans contain no fish. That analogy has been widely quoted because it is accurate and because nothing since has significantly changed the underlying arithmetic. The radio search, which has constituted the vast majority of SETI effort, has several structural limitations that go beyond simple coverage. It assumes that any transmitting civilization is using radio frequencies. Radio is the technology we developed first for long-range communication, and it has genuine physical advantages. It propagates well through the interstellar medium. It is relatively cheap to generate, and its physics is universal, so any civilization that understands electromagnetism would discover it. But these same arguments could have been made for smoke signals or semaphore in an earlier era. A civilization a million years ahead of us in technological development would have moved through the radio stage and into whatever comes next, in the same way that human communication moved through smoke signals and semaphore and telegraph and radio within a single century. The electromagnetic spectrum extends far beyond the radio frequencies that most SETI surveys have monitored. Optical SETI, the search for laser pulses or other coherent light signals, has been an active subfield for decades, but covers a far smaller fraction of the sky with far less total observing time than radio SETI. The rationale for optical communication is strong. Lasers can, in principle, deliver far more information per unit of energy than radio transmissions, and a civilization sophisticated enough to use directed laser communication could transmit enormous data volumes across interstellar distances efficiently. We have been monitoring a tiny fraction of nearby stars for optical pulses for a relatively short time. Beyond the electromagnetic spectrum, there are physically plausible communication channels that we have barely begun to explore. Neutrinos, nearly massless particles that interact so weakly with matter that they pass through the entire Earth with negligible absorption, have been proposed as a communication medium because their penetrating ability would allow signals to be directed through planetary bodies and stellar systems without significant attenuation. We have only recently developed neutrino detectors sensitive enough to detect natural astrophysical sources, and the idea of searching for structured artificial neutrino signals has not moved beyond the theoretical stage. Gravitational waves represent another unexplored channel. The detection of gravitational waves by the LIGO Observatory in 2015 opened a completely new observational window on the universe, one that had been entirely closed for the entirety of human scientific history. Gravitational waves are generated by the acceleration of massive objects, and the production of artificial gravitational wave signals would require engineering on a scale far beyond our current capability. But for a civilization at a sufficiently advanced level of technological development, the same might be said of radio astronomy from the perspective of ancient Rome. We have not searched for structured gravitational wave signals because we have only recently acquired the ability to detect them at all. The most unsettling possibility is that advanced civilizations communicate using physical principles we have not yet discovered. The history of physics suggests that our current understanding, while powerful, is incomplete. Quantum mechanics and general relativity are both extraordinarily successful theories that are also mutually inconsistent, which means neither can be the final word. The physics that resolves their inconsistency, whatever a complete theory of quantum gravity looks like, may involve phenomena that enable communication channels invisible to everything we have built. A civilization with a 10,000-year advantage in fundamental physics would have access to communication technologies as far beyond our current understanding, as radio communication is beyond the understanding of a medieval scholar. The temporal limitation of the search compounds all of these spectral limitations. We have been listening for about 60 years out of a galaxy 13.5 billion years old. If a civilization transmitted signals for 1 million years and then went silent, either from extinction, from transition to a different communication medium, or simply from loss of interest in broadcasting, The window during which we could detect them is 1/10,000th of their transmission lifetime. The probability that any given civilization's broadcasting window overlaps with our listening window, even in the most optimistic scenarios, is subject to the same timing problem that applies to physical contact. The conclusion is not that the Fermi paradox is illusory. Even accounting for all search limitations, there are things we should be able to detect that we have not detected. Megastructures, waste heat, the colonization of entire star systems, that do not depend on narrowband radio searches. But for the specific question of deliberate signals, the negative result from SETI surveys is much weaker evidence for the absence of transmitting civilizations than it is sometimes presented. We have not established silence. We have established that a small fraction of the search space that we have examined in the ways we know how to examine it does not obviously contain what we were looking for. That is a different statement. The absence of megastructures. The search for deliberate signals is sensitive to assumptions about communication technology. The search for megastructures is not. A civilization that harvests the energy of its star, whether through a Dyson sphere, a Dyson swarm, or any other large-scale engineering that intercepts stellar radiation, produces a physical signature that is independent of any decision to communicate. It is waste heat, and it is inescapable. Any process that converts energy produces entropy, and entropy at the temperatures achievable by stellar engineering radiates in the infrared. A star surrounded by an energy harvesting structure would have its optical luminosity suppressed and its infrared luminosity enhanced relative to a naked star of the same type. This signature is not subtle. It is detectable across enormous distances with existing infrared telescopes. In 2015, astronomer Jason Wright led a systematic search for megastructure signatures in data from the WISE Infrared Space Telescope. The survey examined approximately 100,000 galaxies for anomalous infrared excess. The signature expected from a civilization that had reached Kardashev Type 3 status and was harvesting the energy output of a significant fraction of a galaxy's stars. The survey found no candidates that could not be explained by natural astrophysical processes. Not one galaxy in 100,000 showed the specific pattern of suppressed optical luminosity and enhanced mid-infrared emission that a galaxy-scale energy harvesting civilization would produce. The significance of this null result is different in character from the null results of radio SETI surveys. It does not depend on assumptions about which frequencies a civilization chooses to broadcast on, or whether they are trying to communicate at all. The only assumption required is that the laws of thermodynamics apply universally, that any process of energy conversion produces waste heat, regardless of the technology involved. This assumption is as secure as any in physics. The absence of megastructure signatures in 100,000 galaxies is therefore a much stronger statement than the absence of radio signals from a few thousand nearby stars. The constraint applies at the galactic scale. No galaxy within the survey volume showed evidence of Type 3 civilization activity. The survey covered galaxies out to distances of several hundred megaparsecs, encompassing an enormous volume of the observable universe. If Type 3 civilizations exist in any significant fraction of galaxies at the present cosmic epoch, the survey should have detected them. It did not. The upper limit on the fraction of galaxies hosting Type 3 civilizations is extremely small. For Type 2 civilizations, those harvesting the energy of a single star, the constraint is weaker because a single anomalous star would not be detectable in a galaxy-averaged infrared excess measurement. Star-by-star surveys for Dyson sphere candidates in our own galaxy have been conducted using infrared catalogues, looking for stars with anomalously large infrared excesses relative to their optical luminosities. These searches have found some interesting candidates, stars with more infrared emission than expected, but in every case examined in detail, natural explanations involving circumstellar dust have been sufficient to account for the anomaly. No confirmed Dyson sphere candidate exists in the astronomical literature. The most famous candidate for anomalous stellar behaviour, Tabby Star, received its own detailed investigation and is covered in a later chapter. But the broader survey result stands. In the portion of the galaxy we have surveyed with infrared instruments, there is no star whose properties require a megastructure explanation. The galaxy's stellar population, as far as we can tell, consists entirely of naked stars and stars with natural circumstellar material. Nobody appears to be building anything around any of them. The megastructure null result is one of the most powerful constraints in the Fermi Paradox literature precisely because it requires so few assumptions. It pushes strongly against the scenario in which Type 2 or Type 3 civilizations are common. Either advanced civilizations do not build energy harvesting megastructures, which requires explaining why a sufficiently advanced civilization would forgo the energy advantage of stellar scale engineering. Or advanced civilizations are extremely rare, or both. Von Neumann probes and the loudest silence. The megastructure null result constrains civilizations that stay in one place and engineer their home star system. The von Neumann probe argument constrains civilizations that expand, and it constrains them even more severely because the argument requires only that a civilization build one probe at any point in its history, and the mathematics of exponential replication does the rest. John von Neumann, the mathematician who contributed foundational work to quantum mechanics, game theory, and the architecture of modern computers, described in the 1940s the theoretical basis for a self-replicating machine. The concept is straightforward: a machine that can use raw materials from its environment to construct a functional copy of itself. The engineering challenges are substantial, but not obviously impossible. Life itself is a proof of concept for the basic idea, since every living cell is a self-replicating molecular machine. A civilization sufficiently advanced in robotics and materials, science could in principle build a mechanical version. The implications for galactic exploration are staggering. A single von Neumann probe sent to a nearby star system could use the resources of that system, asteroids, metallic ores, ice, to build 2 copies of itself. Those 2 copies travel to 2 new star systems. Each builds 2 more copies, and so on. The number of probes grows exponentially, while the frontier of explored systems expands at a fraction of the speed of light. The mathematics of this expansion have been worked out by multiple researchers, with broadly consistent results. A single probe network launched even at 1% of the speed of light, with replication times of a few centuries per system, could fill the entire Milky Way with probes in somewhere between 1 million and 10 million years. 10 million years is 0.07% of the galaxy's age. The galaxy has been old enough to support this kind of expansion program for billions of years. Any civilization that ever built one probe at any point in the last several billion years should have descendants of that probe in every star system in the galaxy by now, including this one. We have found no probe, no artifact of any kind in the solar system requires an artificial explanation. The Moon, Mars, the asteroid belt, the Trojan points, the Kuiper belt, the Oort cloud, insofar as we have surveyed them, they contain rocks and ice and the unremarkable debris of the solar system's formation. A probe that had been here for millions of years, depending on its design, might have worn down to unrecognizable fragments or might be dormant on a dark rock in a region of the solar system we have not closely examined. The outer solar system in particular is vast and poorly surveyed. There are hundreds of billions of objects in the Oort cloud, and we have directly observed essentially none of them. This observational gap has been taken seriously by some researchers. A paper by Freitas and Valdez in the 1980s explicitly proposed searching gravitationally stable points in the solar system. The Lagrange points where the combined gravity of the Sun and planets creates natural parking orbits for dormant probes. The search was conducted at radio wavelengths with limited sensitivity and found nothing, but the coverage was far from complete. A probe the size of a car with no active emissions in a stable orbit beyond Jupiter would be essentially invisible to current solar system surveys. The absence of confirmed probes, while not as definitively established as the absence of megastructures, remains one of the most challenging aspects of the Fermi Paradox. The probe argument requires no assumption about whether civilizations want to communicate. It requires no assumption about their technology beyond a level that is plausibly achievable within a few centuries of where we are now. It requires only that one civilization, somewhere in the galaxy, at some point in the last several billion years, was curious enough about the universe to send out self-replicating explorers. The silence of the solar system says either that this never happened, or that it happened and the probes are hiding, or that the probes arrived and destroyed the evidence of their own presence. None of these is particularly comfortable. The timing problem. Everything discussed so far has implicitly assumed that civilizations arise throughout the galaxy's history, and that the failure to detect them tells us something about their prevalence or behavior. But there is a completely different class of explanation that does not require civilizations to be rare or dead or hiding. It requires only that they arose at the wrong time, that the distribution of civilization emergence across cosmic time is sparse enough, and the window during which a civilization is detectable is short enough, that the probability of two civilizations being detectable simultaneously is very low. The galaxy is 13.5 billion years old. Humanity has been technologically detectable, radiating radio signals into space for 130 years. If a civilization maintains its technology for 1 million years, before going silent for whatever reason, the fraction of galactic history during which it is detectable is about 0.007%. A randomly chosen moment in galactic history has only a 0.007% chance of falling within any given civilization's detectable window. Two randomly chosen civilizations have a very small probability of being simultaneously detectable. The calculation becomes more specific when you account for the distribution of stellar ages and the time required to develop civilization. The earliest stars in the galaxy formed in the first billion years, but they were almost exclusively very massive stars that burned through their hydrogen and exploded as supernovae within millions of years, without having time to form rocky planets. The elements heavier than hydrogen and helium needed to build rocky planets. The silicon, iron, oxygen and carbon that constitute terrestrial geology and biology had to be synthesized in those first-generation stars and scattered back into the interstellar medium by supernova explosions before they were available to be incorporated into new planetary systems. This enrichment process took time. The oldest rocky planets in the galaxy are probably around 10 billion years old, corresponding to stars that formed about 3.5 billion years after the Big Bang, when sufficient heavy elements had accumulated. A civilization on one of those planets, developing at the same pace as ours, would have achieved radio technology roughly 9.5 billion years ago. Their transmission window, if it lasted 1 million years, closed 8.5 billion years ago. Their signals, expanding outward at the speed of light from a star that is now potentially dead or evolved off the main sequence, have been propagating through the galaxy for billions of years. The leading edge of those signals has long since passed through our region of space. We were not here to receive them. The timing problem compounds when communication delay is factored in. A signal from a civilization 1,000 light-years away takes 1,000 years to reach us. If we detected such a signal and responded, our reply would take another 1,000 years to arrive. The civilization that sent the original signal might have existed, flourished, and gone extinct multiple times during the round-trip communication time. The back-and-forth conversation that we imagine when we think about contact with another civilization requires both parties to maintain continuity of interest and capability across timescales that have no historical precedent in any human institution. No government, no religion, no cultural tradition has maintained uninterrupted organizational coherence for 2,000 years, let alone the tens of thousands of years that communication with a distant civilization would require. The timing problem is arguably not a full solution to the Fermi paradox because it does not explain the absence of megastructures or the absence of von Neumann probes. Physical artifacts that persist long after the civilization that created them has gone silent. But it is a genuine and underappreciated constraint on the signal-based search, and it suggests that even a galaxy teeming with civilizations might be silent to radio searches simply because the windows during which any two civilizations are simultaneously broadcasting are brief relative to the timescales involved. The Transcension hypothesis. Every explanation examined so far, rare earth, hard steps, self-destruction, the zoo, the dark forest, assumes that a surviving advanced civilization would expand outward. More stars, more planets, more territory, more energy. Expansion seems like the natural direction of ambition. It is the direction human civilization has taken since the first migrations out of Africa, and it is the implicit assumption of most Fermi Paradox analyses. If advanced civilizations exist, they should be colonizing the galaxy. The fact that we see no colonization is therefore evidence that advanced civilizations do not exist or do not survive. But futurist John Smart proposed in 2012 that this assumption is wrong in a specific and interesting way. His Transcension hypothesis inverts the standard picture. The natural direction of advanced technological development is not outward into physical space, but inward into increasingly miniaturized, efficient, and computationally dense systems. The trajectory of intelligence is towards smaller, faster, more efficient, not larger. The evidence for this trajectory in our own technology is striking. Computing has followed a consistent path of miniaturization for 80 years. The ENIAC computer of 1945 filled a room, consumed 150 kilowatts of power, and performed about 5,000 operations per second. A modern smartphone fits in a pocket, consumes a few watts, and performs trillions of operations per second. The direction of progress has consistently been toward more computation per unit of volume and per unit of energy. There is no obvious reason to expect this trend to reverse. Extended to its logical conclusion, a civilization that has been following this trajectory for millions of years would have pushed computational density toward fundamental physical limits. The Bekenstein bound derived from black hole thermodynamics sets a theoretical maximum on the information that can be stored in a region of space of a given size and energy. A civilization approaching this limit would be packing more intelligence and more experience into less physical space than we can currently imagine. Their computational substrate might be smaller than a planet, smaller than a city, smaller than a building. And their internal experience, the richness of the virtual worlds they inhabit, and the complexity of the computations they run, would be incomprehensibly greater than anything available in the physical universe. From the outside, such a civilization would be nearly invisible. Its physical footprint would be tiny. Its energy consumption, while large in absolute terms, would be concentrated in a volume so small that its infrared signature might be indistinguishable from a natural compact object. It would not be colonizing star system because it does not need them. It has built a richer universe inside its own computational substrate than the physical universe could provide. The Transcension hypothesis makes a specific prediction about why we have not detected advanced civilizations. They are all around us, but they are so small and so computationally self-contained that they register as nothing. Not as megastructures, not as radio signals, not even as anomalous heat sources. Just as dark matter halos or compact objects or cosmic background noise, invisible in plain sight. The hypothesis is difficult to test, which is its primary scientific weakness. A sufficiently miniaturized and computationally efficient civilization might be genuinely undetectable with any instrument based on macroscopic physics. But it makes a strong prediction in one direction. If the hypothesis is correct, we will never find evidence of large-scale galactic colonization because no advanced civilization goes that route. The galaxy-scale absence of megastructures is consistent with the Transcension hypothesis, though not exclusively predicted by it. The Estivation hypothesis. In 2017, researchers Anders Sandberg, Stuart Armstrong and Milan Čurković published a paper with a title drawn from Lovecraft, That Is Not Dead, Which Can Eternal Lie, proposing one of the most creative and technically grounded solutions to the Fermi Paradox yet developed. The Estivation hypothesis argues that advanced civilizations are not dead, not hiding, and not transcended. They are waiting. Estivation is the summer analogue of hibernation. While hibernation involves dormancy during cold conditions, estivation involves dormancy during hot conditions. Certain amphibians, lungfish and invertebrates estivate when their environment becomes too hot or too dry to support activity, entering a metabolic pause until conditions improve. The Oxford researchers asked what it would mean for a civilization to estivate on a cosmic scale, waiting for the universe itself to cool down. The key insight is thermodynamic. The efficiency of any computation is fundamentally limited by the temperature of the environment in which it runs. The Landauer principle, a result from the thermodynamics of information, establishes that erasing one bit of information requires a minimum energy expenditure proportional to temperature. This means that the same computation can be performed with far less energy in a colder environment than in a warmer one. At the current cosmic microwave background temperature of approximately 2.7 Kelvin, a given amount of energy can support a certain number of computations. In the far future, after the last stars have burned out and the universe has expanded to many times its current size, the background temperature will approach absolute zero, and the same amount of energy could support astronomically more computations. If a civilization's primary goal is to maximize the total amount of computation, the total amount of experience, thought, and information processing, it can perform with a given energy budget. The rational strategy is to conserve that energy during the hot early universe and spend it in the cold far future. A civilization that has amassed a large energy reserve, whether through stellar engineering or some other means, should go dormant now and wake up in 1 trillion years when each unit of energy is worth incomparably more in computational terms. The galaxy is currently in what this framework would call the hot era. Stars are burning. The background is warm. Every computation performed now uses energy that would buy vastly more computation later. An advanced civilization that understood this would not be broadcasting signals or colonizing star systems. It would be compressing itself into the smallest, most stable physical form possible, burying itself somewhere safe and waiting. From our perspective, this would look indistinguishable from absence. The estivating civilizations have not died. They are simply not yet running. The galaxy is a waiting room, full of dormant civilizations counting down to an era of activity so remote in the future that our entire civilization, from the first stone tools to whatever we eventually become, will have been a microsecond of noise in the silence before the real show begins. The Estivation hypothesis received the highest score of any Fermi Paradox solution in a 2021 multi-criteria analysis by Čurković and Vukotić that evaluated 15 major hypotheses across criteria including logical consistency, mathematical rigor, consistency with observational data, and predictive power. It scored 4 out of 5, higher than the dark forest, higher than the rare Earth hypothesis, and higher than most self-destruction scenarios. Its primary weakness is testability. A civilization that is completely dormant and physically compact would produce no detectable signature, but its internal consistency and its grounding in fundamental thermodynamic principles give it a scientific solidity that more speculative hypotheses lack. The sustainability trap. The Estivation hypothesis assumes civilizations are strategically dormant. A related but distinct set of explanations holds that civilizations go quiet, not through strategic choice, but through the inevitable dynamics of unsustainable growth. Any civilization that expands exponentially will eventually encounter the limits of what its environment can provide. When those limits are reached, the expansion stops and often reverses catastrophically. This line of reasoning was formalized in a 2009 paper by Jacob Hack Misra and Seth Baum, who proposed what they called the sustainability solution to the Fermi Paradox. Their argument starts from the observation that exponential growth in a finite system always terminates. This is true of bacterial populations in a petri dish, of human economies in resource-constrained environments, and, the paper argued, of technological civilizations on planets with finite energy and material resources. A civilization that industrializes rapidly burns through its accessible stored energy, the equivalent of fossil fuels, within a few centuries. It alters its planet's chemistry in ways that may destabilize the climate systems that support it. It depletes the easily accessible raw materials needed for manufacturing and construction. At each stage, the civilization faces a choice: adapt, using its intelligence and technology to find solutions, or overshoot, continuing on the same trajectory until the environment collapses under the load. The sustainability trap is not primarily about a single catastrophic event. It is about the difficulty of the adaptation. Transitioning from a high-growth, high-consumption civilization to a sustainable one requires coordinated action across the entire civilization simultaneously. Changes to energy systems, economic incentives, political structures, and cultural values that have never been accomplished in human history at any comparable scale. The prisoner's dilemma structure of resource competition means that individual actors have incentives to continue consuming even when collective restraint would be better for everyone. A 2022 paper by Michael Wong and Stuart Bartlett extended this framework with a concept they called the universal law of civilizational burnout. They argued, drawing on thermodynamics and complexity theory, that every expanding system, biological, economic, or civilizational, follows the same trajectory of accelerating growth followed by collapse or adaptation. Systems that successfully adapt do so by discovering a new stable state at a lower level of throughput. Systems that fail to adapt overshoot and collapse. The fraction of civilizations that successfully navigate this transition, rather than burning bright and dying young, determines whether the galaxy is populated by sustainable, quiet civilizations or littered with the ruins of ones that did not make it. If the sustainability solution is correct, the Fermi Paradox has two answers that apply simultaneously. Civilizations that fail the sustainability test go silent through collapse, becoming undetectable before they ever achieve interstellar communication. Civilizations that pass the sustainability test survive, but do so through restraint, limiting their energy use, their electromagnetic emissions, their physical footprint. A civilization deliberately operating within sustainable limits would be far less detectable than a civilization burning through resources at maximum rate. The galaxy might therefore be populated by quiet, long-lived civilizations that are invisible precisely because they learn to be sustainable. The water world problem. One of the most intriguing and least discussed potential contributions to the Fermi Paradox involves not the development of intelligence, but the physical environment that allows intelligence to translate into technology. The argument is deceptively simple. Intelligence alone is not sufficient to produce a technological civilization. The physical environment must also permit the specific sequence of technological innovations: fire, metallurgy, agriculture, construction, that convert biological intelligence into detectable civilization. Consider the most relevant counterexample from Earth's own biosphere. Dolphins have large brains with a higher encephalization quotient than most mammals. They demonstrate sophisticated problem-solving, social learning, and communication systems of genuine complexity. Octopuses display remarkable cognitive flexibility, tool use, and problem-solving ability. Elephants show evidence of self-awareness, empathy, and long-term memory. None of these species has built a radio telescope or any technology at all. The reason is not cognitive incapacity, but environmental constraint. You cannot make fire underwater. You cannot smelt metal on the ocean floor. You cannot build telescopes or record information persistently, or develop the cumulative technological tradition that produces civilization, without access to dry land and the specific affordances it provides. This observation becomes relevant at planetary scale when the distribution of water among habitable zone planets is considered. Current planetary formation models and the growing catalogue of observed exoplanet densities suggest that a significant fraction of rocky planets in habitable zones are water worlds. Planets whose water fraction is so high that the entire surface is covered by a global ocean, with no continents, no coastlines, no dry land. The water depth on such worlds could be hundreds of kilometres, far too deep for any internal geological processes to push material above the surface. A water world might support life, potentially rich and complex life, in its global ocean. It cannot support fire, which requires both oxygen and a solid fuel in a gaseous medium. It cannot support metallurgy, which requires access to ore deposits at or near the surface and the ability to heat them to thousands of degrees. It cannot support agriculture in the form that drives population growth and surplus production. An intelligent species that evolved in such an ocean, however cognitively sophisticated, would face physical barriers to technological development that intelligence alone cannot overcome. The frequency of water worlds among habitable zone planets is uncertain, but potentially high. The fraction of a planet's mass that is water depends on where in the protoplanetary disk it formed, and how much water was delivered by icy planetesimals during and after formation. Planets that formed in the outer regions of their system and then migrated inward, or planets that received large amounts of cometary bombardment, could end up with water fractions far higher than Earth's. Earth is actually unusually dry by the standards of solar system bodies at its formation distance. The moon-forming impact probably drove off a large fraction of Earth's early water, leaving us with oceans that cover 70% of the surface, rather than the 100% that a wetter planet would have. If water worlds are common among habitable zone planets, some estimates suggest they could outnumber Earth-like planets by a significant margin in certain stellar environments, then the galaxy may be full of biospheres that never produce technological civilizations, not because intelligence does not arise, but because intelligence arises in the wrong medium. Civilizations of the deep, thinking in the dark water, never knowing stars exist. Tabby Star and what it taught us about the search. In 2015, Yale astronomer Tabitha Boyajian led the publication of an analysis of KIC 8462852, a star roughly 1,400 light-years from Earth that had been identified by citizen scientists working through the Planet Hunters program as showing deeply unusual behaviour in Kepler Space Telescope data. Most stars show predictable, periodic dimming when a planet passes in front of them, the transit signal that Kepler was designed to detect. KIC 8462852 dimmed irregularly, by varying amounts over irregular timescales, in a pattern that resembled no known natural phenomenon. The numbers were remarkable. The star's brightness dropped by up to 22% on some occasions, far more than the 1% maximum that even a Jupiter-sized planet could produce. The dimming events were aperiodic. Some lasted days, others weeks. Long-term photometric monitoring suggested the star had also dimmed secularly by a few percent over the course of a century. Nothing in the catalogue of known stellar variability mechanisms fit the data. Jason Wright at Penn State was among the researchers who raised the possibility that the observations were consistent with a partial Dyson swarm, a large number of artificial structures orbiting the star at various stages of construction, unevenly distributed, producing the irregular and deep transit signals. He was careful in his public statements to frame this as a hypothesis of last resort, to be considered only after natural explanations had been exhausted. But the media latched onto the suggestion, and Tabby Star became the most discussed astronomical object in popular science for several years, widely reported as a potential alien megastructure. The scientific investigation that followed was rigorous and ultimately instructive. Extensive multi-wavelength observations were collected across optical, infrared, ultraviolet, X-ray, and radio wavelengths. The key discriminating observation came from comparing the depth of the dimmings at different wavelengths. A solid object, a megastructure, a large planet, any opaque structure, would block all wavelengths of light equally, producing wavelength-independent dimming. Dust scatters and absorbs preferentially at shorter wavelengths, producing dimming that is deeper in the blue and shallower in the red. The observation showed wavelength-dependent dimming. The star dims more in blue light than in red. This is the signature of dust, not a solid structure. By 2018, the scientific consensus had converged on a natural explanation. The star is surrounded by dust, likely from a disrupted comet or a collision in the outer regions of its planetary system. The dust is clumped and asymmetrically distributed, producing the irregular dipping behavior. The secular dimming over a century is consistent with gradual dust evolution. Tabby Star is not a megastructure. The case taught the scientific community several useful lessons about the search for technosignatures. First, anomalous data should be investigated thoroughly rather than dismissed or immediately attributed to extraordinary causes. The scientific process worked exactly as it should. An unusual observation was taken seriously. Competing hypotheses were developed, and systematic observations discriminated between them. Second, multi-wavelength observations are essential for distinguishing between natural and artificial explanations, because the physics of materials provide specific wavelength-dependent signatures that constrain what the obscuring material can be. Third, and perhaps most importantly, the episode demonstrated that even a star with the most anomalous behavior in a catalogue of 150,000 Kepler targets turned out to have a natural explanation. The bar for a confirmed technosignature detection is high, and meeting it requires systematic multi-wavelength characterization. Fast radio bursts and the limits of interpretation. In 2007, astronomer Duncan Lorimer discovered in archival data from the Parkes Radio Telescope in Australia a signal of extraordinary character. A single burst of radio emission lasting a few milliseconds, arriving from a direction far outside the Milky Way, with a dispersion measure, the frequency-dependent delay caused by free electrons in the intergalactic medium, indicating an origin billions of light-years away. The total energy released in those milliseconds was comparable to what the Sun emits over an entire day, in a flash shorter than an eye blink. The Lorimer burst, as it became known, was initially treated with suspicion by much of the astronomical community. Single detections of anomalous signals have a history in radio astronomy of turning out to be instrumental artifacts or local radio frequency interference. A notable example at the Parkes telescope itself was the detection of what appeared to be peculiar radio bursts that turned out to originate from a microwave oven in the observatory kitchen being opened before the magnetron had fully powered down. Caution was warranted, but more bursts appeared, not from microwave ovens, from all directions in the sky, arriving from extragalactic distances, some repeating from the same location, most appearing only once. By 2025, astronomers had catalogued thousands of events, now called fast radio bursts, and the statistical properties of their distribution, isotropic on the sky, extragalactic distances indicated by dispersion measures, energy scales consistent across many events, established beyond reasonable doubt that they were a genuine astrophysical phenomenon rather than instrumental artifacts. The leading physical explanation involves magnetars, neutron stars with extraordinarily powerful magnetic fields, among the strongest known in the universe. When a magnetar's crust fractures under magnetic stress, or when its magnetic field undergoes a rapid restructuring, the energy released can produce a burst of coherent radio emission with properties consistent with observed fast radio bursts. The evidence for this explanation was substantially strengthened in 2020 when a fast radio burst was detected from SGR 1935 +2 154, a known magnetar within our own galaxy, with properties matching those of extragalactic fast radio bursts. The magnetar explanation accounts for the majority of observed events. But science requires honesty about what has and has not been established. A minority of fast radio bursts show properties, particularly certain repeating bursts with complex time-frequency structure, that do not fit simply into the magnetar framework. Some repeating sources show apparent periodicity in their burst activity, with active and inactive windows that repeat on timescales of days to weeks. The physical mechanism producing this periodicity within the magnetar framework requires additional explanation, typically involving precession of the magnetar or orbital modulation by a companion. Harvard astrophysicist Avi Loeb and colleagues published papers exploring whether some fast radio burst properties could be consistent with artificial origin, specifically the leakage radiation from a civilization using powerful microwave beams to propel spacecraft by light sail. The physical requirements for such a propulsion system at interstellar scales would produce bursts with some properties similar to what is observed. Loeb was careful to present this as a hypothesis requiring investigation rather than a conclusion, and the scientific consensus has not moved toward artificial origin for any known fast radio burst source. What fast radio bursts actually demonstrate in the context of the Fermi Paradox is the importance of interpretive caution. The universe contains natural phenomena that can superficially resemble what artificial signals might look like. The detection of an anomalous signal is not itself evidence of artificial origin. A confirmed technosignature requires ruling out all natural explanations, not merely identifying that natural explanations are incomplete or imperfect. The fast radio burst story, anomalous discovery, community skepticism, accumulation of evidence, convergence on natural explanation, with residual uncertainty for some cases, is the template for how any future technosignature candidate should be handled. The WOW signal. On the night of August 15, 1977, the Big Ear radio telescope operated by Ohio State University recorded a signal that has never been explained to the satisfaction of the scientific community and has never been confirmed. The telescope was scanning the sky as part of a systematic SETI survey, recording the intensity of radio emissions at frequencies near the hydrogen line. 1420 MHz, the natural emission frequency of neutral hydrogen, long considered a logical candidate for interstellar communication because it is universally known to any civilization that has discovered radio astronomy. The hydrogen line was not an arbitrary choice. It sits in a region of the radio spectrum sometimes called the cosmic watering hole, a band of frequencies between the hydrogen line and the hydroxyl radical emission line at 1720 MHz, flanked by two of the most abundant molecules in the universe. The logic was that any civilization attempting to communicate across interstellar distances would choose a frequency that the intended recipient could reliably identify as significant. And the most universally significant frequencies are those associated with the most abundant chemistry in the cosmos. Most nights produce nothing but the thermal background noise of the sky. On this night, the telescope recorded a signal so strong that when astronomer Jerry Aman reviewed the computer printout a few days later, he circled the sequence of characters representing its intensity and wrote a single word in the margin: wow. The signal's strength was 30 times the background noise level. It appeared at the expected frequency. It rose and fell in intensity over 72 seconds, in a pattern perfectly consistent with a point source passing through the telescope's beam as the Earth rotated, exactly how a deep space transmission would behave. It came from the direction of the constellation Sagittarius. The Big Ear telescope had two feed horns that scanned different parts of the sky separated in time. The wow signal appeared in only one of the two horns, which is consistent with a genuine localized source rather than local interference. Local interference would typically appear in both horns. It never occurred. Aman and his colleagues pointed the Big Ear at the same location dozens of times in the months and years afterward. Other telescopes joined the search. The Very Large Array, the Arecibo Observatory, and several other facilities conducted dedicated follow-up observations targeting the same region of sky. No subsequent detection has ever been made at that location. For a scientific result to be accepted, it must be reproducible. A single observation that cannot be repeated cannot be confirmed. This is not an arbitrary standard of rigor. It is the minimum requirement for distinguishing a genuine astrophysical event from an instrumental artifact, a data reduction error, or a statistical fluctuation in noise. Several natural explanations have been proposed over the decades. In 2017, a paper by Antonio Paris proposed that two comets, 266P/Christensen and P/2008Y2, were in the vicinity of the wow signal's source direction at the time of detection, and that hydrogen outgassing from comets could produce emission at the hydrogen line frequency. The paper attracted significant attention and some acceptance in the popular science media, but it was criticized by other researchers on technical grounds. The calculated brightness temperature of the comet outgassing was orders of magnitude too low to produce a signal as strong as the wow detection. Comets were known to the SETI community when the hydrogen line frequency was chosen as a search frequency, and their hydrogen emission had been considered and rejected as a practical problem for exactly this reason. It is far too faint to masquerade as an interstellar signal. A signal 30 times above the noise floor at the Big Ear's sensitivity cannot be explained by cometary outgassing under any reasonable model of cometary hydrogen emission. The comet hypothesis also fails to account for the signal's narrow bandwidth. Cometary emission is broadband, while the wow signal was narrow enough to be consistent with an artificially generated carrier wave. Critics of the Paris paper noted additionally that the comet positions at the time of the signal, while in the general region of Sagittarius, were not precisely consistent with the signal's measured right ascension. The wow signal remains the strongest candidate for a potential extraterrestrial transmission in the recorded history of SETI. It satisfies more of the criteria for what an alien signal might look like than any other observation on record. the right frequency, the right intensity profile, the right celestial mechanics, the right directionality, and the right bandwidth narrowness for an artificial origin. It also remains completely unverified, which in science means it cannot be treated as a confirmed detection of anything. What makes the WOW signal a genuinely interesting Fermi Paradox data point is not the probability that it was artificial, which cannot be assessed from a single unrepeated observation, but what it illustrates about the structure of the problem. If an advanced civilization transmitted a signal powerful enough to be detectable across interstellar distances, and if that transmission was brief or intermittent, rather than continuous, the probability that our brief window of listening would happen to coincide with one of those transmissions is very small. We might receive one such signal and never receive it again simply because it was not a continuous beacon, but a brief directed transmission or a regular broadcast that we happened to catch once and have not been listening at the right moment since. The Big Ear itself was decommissioned in 1997. The very telescope that recorded the signal no longer exists. Follow-up observations have been conducted with other instruments, but the specific combination of beam size, frequency coverage, and sky position that enabled the original detection has not been exactly replicated by any subsequent search. The WOW signal therefore illustrates both the tantalizing possibility that something has reached us and the structural difficulty of confirming it. The silence since 1977 does not prove the signal was not artificial. It proves that if it was artificial, the source was not broadcasting continuously toward Earth. And a source that broadcasts intermittently is, from our perspective, mostly silent. The silence and the signal are not necessarily contradictory. In nearly 50 years since the detection, no natural explanation has been confirmed, and no artificial explanation has been confirmed. The signal remains precisely what Neumann's annotation suggested it was, something that warranted attention, whose ultimate nature remains unknown. What Technosignature science actually shows. The search for extraterrestrial intelligence has been expanding beyond radio signals for several decades, and the broader field of Technosignature science, the systematic search for any observable consequence of the existence of a technological civilization, has developed a more comprehensive and more physically grounded framework for thinking about what detectable signatures an advanced civilization might produce. The expansion is not merely a broadening of the search to cover more frequencies or more sky. It is a fundamental reconceptualization of what we are looking for and why, moving from the assumption that civilizations communicate deliberately toward the recognition that civilizations leave physical imprints on their environments that are detectable regardless of intent. A technosignature is any observable departure from natural astrophysical expectation that could be produced by technological activity. Radio signals are one class of technosignature, megastructures are another, but the range extends considerably further. Industrial pollution of a planetary atmosphere, the presence of specific molecules that are produced by technological processes, but not by biological or geological ones, is a technosignature that could potentially be detected in the atmospheric spectra of nearby exoplanets. Chlorofluorocarbons are a particularly clean technosignature because they have no known natural production pathway. They are uniquely the product of industrial chemical synthesis. Their presence in a planetary atmosphere at detectable concentrations would be unambiguous evidence of industrial activity. Nitrogen dioxide at concentrations above what photochemistry and lightning can produce is another industrial marker. Sulfur hexafluoride, used extensively in electrical equipment, has essentially no natural source. Night side illumination of a planet, artificial lighting visible on the side of a planet facing away from its star, is a technosignature that future extremely large telescopes might detect for nearby systems, analogous to seeing city lights on the dark side of the Moon. The spectral signature of propulsion systems, whether rocket exhaust or laser sail drivers, is a technosignature. The modification of a planet's albedo through large-scale surface construction, solar panels, cities, agricultural monocultures, is a technosignature measurable through precise photometry of a planet's reflected light. The James Webb Space Telescope has already demonstrated that atmospheric characterization of exoplanets is achievable at a level of detail that was theoretical a decade ago. Its detection of carbon dioxide and methane in the atmosphere of K2-18b, a sub-Neptune planet in the habitable zone of a red dwarf star, demonstrated that atmospheric chemistry can be measured for planets in habitable zones at distances of tens of light years. The same technique, applied to a rocky planet with a technological civilization that has been industrializing for a few centuries, might detect elevated concentrations of chlorofluorocarbons, nitrogen oxides, or other industrial byproducts. The sensitivity of current instruments is not sufficient for this measurement on Earth-sized planets at the distances of the nearest stars. The signal-to-noise ratio for an Earth twin around the nearest Sun-like star would require impractically long integration times with Webb. But the Habitable Worlds Observatory currently in development is being specifically designed to bring this measurement within reach for planets around the nearest dozen or so Sun-like stars. It represents the first instrument whose design specifications were set with the explicit goal of detecting industrial technosignatures on Earth-sized worlds. The systematic nature of the technosignature search has been formally evaluated in a series of workshops organised by NASA and the SETI Institute. A 2020 report published by this community mapped the full parameter space of potential technosignatures, estimated the sensitivity of current and near-future instruments to each class of signature, and identified the highest priority searches given available resources. The report's conclusion was that the search was severely resource-limited, that compelling searches for several classes of technosignature were achievable with modest investment, but had not been conducted simply because the funding and telescope time had not been allocated. The total funding devoted to SETI research in the United States in any given year is less than the cost of a single night on a major ground-based telescope. The search for what might be the most important discovery in human history has been conducted on the budget of a small university research program. The most important finding from the technosignature literature is the systematic one. When the full range of potential signatures is considered and the current survey coverage of each is assessed, the fraction of relevant parameter space that has been searched is uniformly tiny. Not just for radio signals, for every class of signature that physics allows. Industrial atmospheric pollution has been searched for in essentially zero exoplanet atmospheres at the sensitivity needed to detect Earth-level signals. Night-side illumination has never been searched for systematically. Laser pulse signals have been searched for in only a fraction of nearby stars on limited timescales. The absence of confirmed detections cannot currently be interpreted as strong evidence for the absence of technological civilizations, because the search depth is nowhere near sufficient to support that conclusion. This does not mean the Fermi Paradox is solved by appeal to observational incompleteness. The megastructure constraint, the von Neumann probe argument, and the large-scale infrared survey of galaxies provide constraints that are robust against most observational incompleteness arguments. A galaxy-spanning Type 3 civilization cannot be hidden by incomplete surveys. Its energy budget would be too large to miss. But for civilizations at our level, or modestly above it, the honest statement of what technosignature science shows is, we have searched a small fraction of the relevant parameter space and found nothing in that fraction. The rest remains unsearched. Conclusions about cosmic solitude drawn from this search history are, by the arithmetic of what has actually been examined, premature. The SETI paradox. There is an irony embedded in the search for extraterrestrial intelligence that rarely receives the attention it deserves. The assumptions underlying the design of most SETI searches are in tension with the behavior of the only technological civilization we know anything about, our own. The search was designed in the 1960s based on extrapolations of 1960s technology, and the actual trajectory of technological development has gone in a different direction from the one the design assumed. SETI searches assume that an advanced civilization would be detectable because it would be broadcasting powerful signals into space, either intentionally as a beacon or unintentionally as leakage from internal communications. This assumption was reasonable in the 1960s when the search began, because the trajectory of human communication technology at that time pointed toward increasingly powerful transmitters and increasingly widespread broadcasting. Radio and television stations were proliferating. Radar systems were becoming more powerful. The electromagnetic footprint of human civilization was growing rapidly, and it seemed natural to extrapolate this trajectory forward and outward. A civilization more advanced than ours would be broadcasting more powerfully, not less. But the actual trajectory of human communication technology has gone in the opposite direction. The transition from broadcast radio to cable television reduced the amount of energy beamed into space from entertainment transmissions. The transition from analog to digital communication reduced power requirements further while increasing information density. The shift to fiber optic cables for data transmission and to low-power local wireless networks for short-range communication means that the electromagnetic leakage of human civilization is now decreasing rather than increasing, despite a massive increase in total information processing and total communication bandwidth. Our civilization is communicating more than ever and leaking less radiation into space than it was 30 years ago. A civilization monitoring Earth from a nearby star system that had been detecting our radio leakage since the mid-20th century would have seen our electromagnetic footprint rise through the broadcast era, peak sometime around the 1980s or 1990s, and then begin declining as our communications migrated to lower power and more directed channels. Projection forward, it is plausible that within a few more decades, the deliberate use of directed laser communication, quantum communication channels, or other high-efficiency modalities will further reduce the radio frequency leakage of human civilization toward essentially zero. Laser communication concentrates all transmitted energy into a narrow beam pointed precisely at the intended recipient, producing no detectable leakage in any other direction. Quantum key distribution and quantum communication more broadly are inherently directional and low power. A civilization a few centuries more advanced than us in communication technology might be essentially electromagnetically invisible to an omnidirectional receiver, not by choice, not by strategic decision, not by deliberate concealment, but simply as a consequence of using communication technology that is more efficient and therefore less leaky. Efficiency and detectability are inversely related, and efficiency is the direction that technological development consistently moves. This has direct implications for the design of SETI searches. If the most advanced civilizations are precisely the ones with the smallest electromagnetic footprint, because efficiency reduces leakage, then the brightest targets in a radio SETI survey are civilizations at roughly our current level of development, too weak to detect at interstellar distances, while the most powerful civilizations are the dimmest. The search strategy that logic suggested in the 1960s may be systematically biased toward the least informative targets. We are most likely to detect a civilization in a brief developmental window similar to our own, which is also the window during which civilizations are least capable of being interesting interlocutors. The civilizations that have had millions of years to develop and that might have answers to deep questions are precisely the ones that our search strategy is least likely to find. The SETI paradox does not mean the search is futile. Intentional beacons, signals specifically designed for maximum detectability, not leakage, but deliberate transmission, would not follow this efficiency argument. A civilization that wanted to be found could still broadcast a powerful signal regardless of the efficiency of its internal communications. But designing an intentional beacon requires a decision to broadcast, a decision about which frequencies to use, a decision about which directions to point, and a sustained commitment to broadcasting for long enough that a developing civilization in the target region reaches technological capability during the broadcast window. Whether any advanced civilization makes all these decisions correctly and sustains them for the required duration is itself an unknown. The assumption that powerful leakage radiation would make advanced civilizations detectable appears, on reflection, to be based on an extrapolation of our own early-stage communication technology that does not hold for more mature technological development. The window during which a civilization leaks detectable radio energy may be very narrow, perhaps only a century or two, before efficiency improvements close it permanently. What evidence would actually look like? Given everything that has been established about the difficulty of detection and the range of possible technosignatures, it is worth being precise about what a confirmed detection of extraterrestrial intelligence would actually require. The criteria are more demanding than popular discussions typically acknowledge, and understanding them clarifies both what has and has not been established by current searches and what future searches need to accomplish. The history of premature detection claims in the field makes precision about the confirmation standard essential. A confirmed technosignature detection requires several properties simultaneously. The signal or artifact must be reproducible. It must be detectable on repeated observations, not just in a single instance that might reflect instrumental error, data reduction artifacts, or statistical fluctuation. Reproducibility is the foundational requirement of empirical science, and it is the requirement that has defeated every previous candidate. It must be inconsistent with all known natural explanations at a high level of statistical confidence, not merely unexplained, but demonstrably inconsistent with natural processes. This is a higher bar than it appears, because the universe is physically rich enough that many natural phenomena are poorly understood and could in principle account for anomalies that seem artificial at first examination. It must have properties that require intelligence, that reflect information content, deliberate structure, or physical characteristics that could not arise from the known processes of astrophysics, geology, or chemistry. Narrowband radio emission is not by itself a signature of intelligence. Masers produce narrowband emission naturally. What would be a signature of intelligence is narrowband emission that encodes mathematical structure, or that uses a modulation scheme consistent with information encoding, or that varies in a way that is inconsistent with any known natural variability mechanism. And it must be verifiable by independent groups using independent instruments and methods, because the history of anomalous astrophysical signals includes numerous cases where the anomaly turned out to be specific to one instrument, one analysis pipeline, or one observer's interpretation. The wow signal fails the first criterion. Despite nearly 50 years of follow-up attempts, no confirmed repeat detection has been made at the same location and frequency. Tabby Star ultimately failed the third criterion. Multi-wavelength observations demonstrated that the dimming was wavelength dependent in the manner expected of dust rather than solid structures, eliminating the megastructure interpretation at the level of physical consistency. No detected fast radio burst has yet been shown to satisfy the second. The magneto explanation accounts for the observed properties of all well-studied examples, and no burst has shown properties demonstrably inconsistent with all natural explanations. The 1996 announcement of possible microfossils in the Martian meteorite ALH 84001 is the most relevant case from astrobiology rather than SETI. It failed both the second and third criteria under sustained scrutiny, with every proposed biosignature, the putative nanofossil structures, the magnetite crystals, the polycyclic aromatic hydrocarbons, finding natural mineral and chemical explanations that the original authors had not adequately excluded. The history of candidate detections in astrobiology and SETI is a history of claims that did not survive rigorous testing. This is not a failure of the field. It is the field working correctly. Science requires that extraordinary claims withstand extraordinary scrutiny, and the claim of confirmed extraterrestrial intelligence is among the most extraordinary possible. The appropriate response to each candidate is not dismissal, but investigation, and the investigation has consistently produced natural explanations. What this history demonstrates is that the confirmation process is long, requires multi-instrument follow-up, demands expertise across multiple fields simultaneously, and produces conclusions that are initially uncertain and gradually convergent rather than immediately decisive. The first confirmed technosignature will not be announced on the night of detection. It will be the product of years of systematic follow-up work that eliminates alternatives one by one. The next generation of instruments, Webb's atmospheric characterization capability, the Square Kilometre Array's radio sensitivity, the Habitable Worlds Observatory's direct imaging capability, will push the sensitivity frontier significantly. If a rocky planet within 10 parsecs has industrial pollution at the level of Earth's current atmosphere, the Habitable Worlds Observatory should be able to detect it in a reasonable integration time. If a civilization within a few hundred light years is broadcasting a powerful continuous beacon on any frequency the SKA covers, the SKA should detect it with high confidence. The Vera Rubin Observatory's Legacy Survey of Space and Time will systematically monitor billions of stars for variability, providing sensitivity to the kind of irregular dimming that might indicate large-scale stellar engineering. The era of comprehensive search is not yet here, but it is beginning. What confirmation would look like is different from what detection would look like. Detection is identifying an anomalous signal or artifact. Confirmation is eliminating all natural explanations to the scientific community's satisfaction, a process that requires time, resources, and the organized skepticism of multiple independent research groups. The experience of ALH 84001 and Tabby Star suggests that even very promising candidates require years of systematic follow-up work before the scientific community converges on a conclusion. Any future detection should be expected to generate the same process: immediate excitement, rigorous investigation, and either the eventual elimination of natural explanations or, for the first time in history, their sustained failure to account for what is observed despite exhaustive effort. The confirmation of extraterrestrial intelligence will not be a moment. It will be a process. The most honest answer. After more than 70 years of scientific engagement with the Fermi Paradox, what does the field actually know? What can be said with genuine confidence, and what remains irreducibly uncertain? The question deserves a direct answer that does not retreat into false equivalence between better and worse supported hypotheses, but also does not overstate the certainty that the available evidence supports. What is known with confidence? The galaxy is old enough and large enough that at least one spacefaring civilization, if any has ever existed, should have colonized it entirely multiple times over by now. No evidence of galactic-scale colonization exists, no megastructures in infrared surveys of 100,000 galaxies, no anomalous stellar engineering signatures in our own galaxy, no confirmed probes in the solar system, no unambiguous technosignatures of any class despite searches across multiple wavelength ranges. The silence is real in the sense that the absence of obvious large-scale signatures is established beyond any reasonable dispute. A galaxy-spanning civilization of the kind that straightforward application of the Drake equation predicts should produce does not appear to exist in the observable universe. This requires explanation. It is not a possible finding that might emerge from better data. It is an established finding that any complete theory of civilization in the universe must account for. What is genuinely uncertain? Whether the explanation is the rarity of life, the rarity of intelligence, the self-destruction of technological civilizations, the deliberate silence of existing civilizations, or some combination of these operating at different frequencies and different cosmic epochs. The honest assessment of each leading hypothesis is that none has been confirmed and none has been definitively excluded. The rare Earth hypothesis correctly identifies that many conditions Earth satisfies may be uncommon, but the quantification of how uncommon is poorly constrained. We do not have sufficient sample sizes of planetary systems at different stages of evolution to say whether Earth's specific combination of conditions is 1 in a million or 1 in a trillion. The Great Filter framework is logically airtight, but does not identify the filter. It tells us that something prevents visible civilization without specifying what. The self-destruction hypotheses are physically plausible and historically suggestive, but undemonstrated as universal. One civilization narrowly survived the nuclear age so far, which is insufficient evidence that all civilizations fail it. The deliberate silence hypotheses are logically coherent but structurally resistant to testing. They predict continued silence regardless of whether their specific mechanism is real. The most important epistemological constraint on the field is negative. No hypothesis can currently be dismissed as impossible on observational grounds. The range of viable explanation spans the full distance from we are the only technological civilization that has ever existed in the Milky Way to the galaxy is full of civilizations that are either dormant, transcended, or hiding with sufficient skill that our primitive instruments cannot detect them. Both ends of this range are consistent with the current observational record. The data do not discriminate between them. This is an uncomfortable conclusion for a scientific field, but it is the honest one. The Fermi Paradox is not solved. It is a boundary condition on theories of civilization whose solution requires data we do not yet have. The most important thing the next generation of instruments will establish is the value of the biological terms in the Drake equation, the abiogenesis fraction and the complexity evolution fraction that have been unknown since 1961. If life is found on Mars, even microbial fossils in ancient rock, the abiogenesis filter is removed as a candidate behind us explanation. If complex chemistry consistent with biology is found in Europa's ocean or Enceladus's plumes, the same. If biosignatures are detected in the atmosphere of a nearby exoplanet by Webb or the Habitable Worlds Observatory, the conclusion that life is widespread follows with high confidence from the statistics of how few systems have been examined. Each such discovery narrows the range of viable explanations and pushes the filter forward away from biology and toward either intelligence, technology, or something we have not yet identified. If extensive searches find no biosignatures anywhere, on Mars, in the outer solar system, in the nearest stellar systems, the filter may genuinely be in the early biological steps, and the galaxy's silence is the silence of chemistry that almost never becomes biology. The most honest summary of the current state of knowledge is this: the Fermi Paradox is a real, quantitatively established and unresolved scientific problem. The silence is genuine and requires a causal explanation. The field has identified multiple physically coherent explanations across the biological, physical, sociological, and thermodynamic domains, and has ruled none of them out with the data currently available. The searches conducted so far are insufficient in breadth, depth, and wavelength coverage to discriminate between the leading hypotheses. The next 2 or 3 decades of observations with Webb, the SKA, the Habitable Worlds Observatory, the Vera Rubin Observatory, and the maturing Technosignature search program will provide the first data capable of testing the leading hypotheses in a scientifically meaningful way. We do not yet know why the galaxy is silent. We are beginning, for the first time in the history of the question, to build instruments capable of finding out. That is not a small thing. It is the beginning of an answer. The shape of silence. There are 3 things that could be true about the galaxy, and each one changes the meaning of everything. The first is that we are alone, that the sequence of events that produced life on Earth, then complex cells, then animals, then intelligence, then technology was so improbable that it has not happened anywhere else in the observable universe, that the 400 billion stars of the Milky Way and the 2 trillion galaxies beyond it have produced in all their history exactly one species capable of asking where everyone is. If this is true, the weight of it is almost insupportable. Every thought ever thought, every discovery ever made, every piece of music ever composed exists only here, is known only here, and will end only here. The universe is not empty. It is full of gas and fire and stone and radiation and time. But of minds, of the thing that makes the universe aware of itself, there is only us. And every choice we make about our weapons, our climate, our machines, carries the full weight of that singularity. The second is that we are early, that the galaxy is not a graveyard, but an empty nursery, that most of the civilizations that will ever exist have not yet been born, that we are among the first, pioneers in a cosmos that is only beginning to develop the complexity it will eventually achieve. If this is true, the choices we make now carry a weight that no previous generation of humans has had reason to consider. We are not just deciding the fate of one species on one planet. We are setting the precedent for what intelligence does, whether it survives, whether it expands, whether it is benevolent, for every species that follows us into the universe. The first civilization to reach the stars will shape what the galaxy eventually becomes. The third is that we are watched, that the silence is not the silence of absence, but the silence of restraint, of civilizations that exist, that know we are here, and that have chosen not to speak for reasons that may be protective or strategic, or simply beyond our current comprehension. If this is true, then the universe has a sociology we have not yet been invited to join, and whatever test we may be undergoing is one whose criteria we have not been told. What is striking about all 3 possibilities is that they converge on the same practical conclusion. Whether we are alone, early, or watched, the argument for ensuring the survival and continued development of our civilization is identical. If we are alone, our survival is the survival of the only mind in the observable universe. If we are early, our choices define the template for all that follows. If we are watched, our behavior may be precisely what determines whether the silence ever breaks. The Fermi Paradox began as a question asked over lunch. It has become, in the 75 years since, one of the most productive open problems in science. Productive not because it has been answered, but because the attempt to answer it has driven advances in cosmology, astrobiology, evolutionary theory, game theory, information theory, and the philosophy of mind. Every proposed explanation has sharpened our understanding of what life requires, what intelligence is, what civilizations do with power, and what the future might hold. The question has illuminated more by remaining open than most questions illuminate by being closed. The silence is not an absence of information. It is the most important data point we have. We just have not yet learned to read it. Where is everybody? We do not know. But for the first time in the history of the question, we are beginning to build the tools to find out. The answer, when it comes, will be the most important thing science has ever told us, regardless of what it is.